Okay, I think I just went one step further than I really wanted to, so I'm going to cross this out for a moment. Okay? If you see the equation that looks like this, no, what I did here was just stupid. Okay? This would equal 1, not 0. If I divide both sides by this, I don't get 0 over here, do I? Okay? So I was just stupid there. Okay? So if I uncross this, I would get something like dy dt equals y sine t minus 2t over cosine t. Now I don't have to cross this out, but I already did. Okay? So, writing 0 there, I don't know why I wrote 0. I wasn't thinking. And like I said, I wasn't paying enough attention, so I did something dumb. But this equation is then the same as this one, right? So now you got your y prime equals this. This is not separable, and it's not, I've got a y in here. Can't separate the y's from the t's. Okay? Go ahead and try, you can't do it. So, if you see this equation, what in the world are you going to do? Or if you see this equation, what in the world are you going to do? Well, you might try a bunch of different things, but I don't think they're going to work. Okay? So you test to see whether this thing is exact. Now we know it is because it comes from df equals 0 for this function, right? Assuming I didn't make another ignorant error in my algebra, okay? Make sense? How do you test this to see if it's exact? Elam, you should know. You've had multivariable calculus, you did something very similar, but you probably won't recognize it until I show you. Oh, you look like you're thinking. Go ahead. Got an idea?
It looks an awful lot like Green's theorem, but...
Yeah, it's good that it invokes that, but it's not quite it. Okay, I'm going to show you, then you'll see. Ready? Okay, if this equation be written like this, which still looks a lot like Green's theorem, doesn't it? Kind of invokes Green's theorem. That's not what we're doing with it. It's not right now. Okay, we've got this. Or mx equals ny. Now why does mx equal ny? Well, what's m? It's in front of dy, right? Go back here. What's in front of dy? df dy, right? I'll write fy, meaning y derivative of f, so I don't have to write as many symbols. And n is fx, right? Yeah. So what's mx? Well, m is fy, right? Okay, well, that's your test now. So you're going to call this M, you're going to call this N, and you're going to test whether mx equals ny. If it is, then you can integrate it. Okay? So the test.
So that's supposed to be dt instead of dx.
Yeah, I'm using x and t interchangeably as the dependent variable. It's generally written in terms of x and y. I started writing in terms of t, but to avoid confusion, okay. Now over here I'm using x instead of t, but you're going to see it both ways and that shouldn't hurt you. Okay? You can reason it out using x instead of t and you get the same test. Okay? And since I wrote it in terms of dy and dx, which I think is the way your book does it. Okay? But there's no reason it couldn't be written using t instead of x. Okay, so anyhow, you got this, right? Now, is it true that for the equation cosine t dy plus 2t minus sine t y sine t dt equals 0, okay, you're going to take the x derivative of m, but we're using t, so it'll be the t derivative. mt is negative sine t. And y is what?
Negative sine t.
Yeah. Has to be, because of course, how did we get m and n? We started with a function that took its differential to get this equation, right? So we know the equation comes from a differential. Okay? Now, if this condition holds, then the equation came from a differential. Okay? And if the equation came from a differential, this condition has to hold. Okay, you want to prove that with some general symbols, but that's the way it is. Okay? Okay, so how do we recover our original f function, assuming we don't know it? Well, remember m is fy, right?
So is this like testing if a vector field has a potential function? Finding the potential function?
Again, those are good associations, not quite, but maybe. I have to think that through. But let's do this. Okay, think that through. Think through if that's true. And so well, if m is the y derivative of f, then f is the integral of m and integral of m with respect to y, right? And m is cosine t. Right? In the integral of cosine t with respect to y, well, cosine t is regarded as a constant. When you, it doesn't have any y dependence. So when you integrate with respect to y, this is regarded as just a constant with respect to y, right?
So it's y cosine t plus function of t.
Yep. And you remember that from multivariable, right? Okay. So plus some g of t, because any function of t would be immune. Okay? Now, Alexander, since you haven't had multivariable, you're not that familiar with this, or with partial derivatives, so I'm going to, phrase some problems to make it clear what's going on. Okay? But everything up to here where you test it is pretty straightforward. Okay? Still, I want to phrase some problems for you just to get you up to speed on that, because there's very little that is done in multivariable calculus that's useful, directly useful in differential equations. Okay? Although there are relationships, and Elam has referred to several of them. Okay? So we're not going to leave you hanging out there over the abyss on this. I'll give you a little bit of work, not much, an hour's work.
Yeah.
Unless you can't do the calculus.
Then it'll be fine.
But I'll keep the calculus relatively simple, just to give you the idea. Okay, so we get this, right? And
Physics is like
so
it's calculus is too.
wrong, they'll be fixing it, spend 3 days fixing it.
so f is going to be an integral of n dt, right? Now I'm writing x's, and where did I write an x? Yeah, n is f t. Okay. I've got something backwards, so that doesn't work. That does. I integrate n with respect to t. Never mind. I have the wrong f in mind. Okay, so that equals an integral of 2t minus y sine t dt. I probably should have gone up to more board space there, but antiderivative of 2t is clearly t squared, right? And we notice that our f function had a t squared in it, right? So that's going to match, as does the y cosine t, because our original f function, just to remind everybody, is y cosine t plus t squared, right? Now we already got the y cosine t, and now we're going to get the t squared, right? But everything else we've got had better match. So integrating 2t, we get t squared. And then minus y sine t dt, what's the antiderivative? Regard y as a constant, your antiderivative of the sine is negative cosine, and you got a negative. So this is plus y cosine t plus a function h of y, in case we need it, but we don't.
It's just a constant, right?
Okay, now these reconcile, they both have the y cosine t, right? Now what does this one have that this one doesn't? Well, it has a t squared, right? That's just your g of t, because any g of t function is constant with respect to integration on y, or differentiation with respect to y, right? Okay? So we needed the g of t function to account for the t squared. If there was some function solely of y up here, we would have needed the h of y function to accommodate it. Okay? But there isn't, so everything reconciles. And we get f of ty equals y cosine t plus g of t, and that has to equal t squared plus y cosine of t plus an h of y. Okay? Now, these reconcile if g of t equals t squared and h of y equals 0. And again, that has to happen if the equation is exact. This all has to work out. So your f of ty is y cosine t plus t squared.
Isn't h of y equal to c? Any constant?
Equal to what?
Any arbitrary constant?
No. No, there's no, wait a minute. Yeah, h of y doesn't have to be 0. So h of y could be c. And of course you have to get an integration constant, so I shouldn't have left that out. Okay? So our equation, our differential equation, that we pretended not to know when we started, but that we got from setting df equal to 0, is differential of this so that f of ty equals c. Now we're going to see that we really didn't have to put a c in there because you're going to get it from this. Okay? So really, if you don't put an arbitrary constant in there because you get one when you do this. And you don't need two of them. And if you have one here and one here, well, you just add them together and they absorb. Right? Okay? So we really didn't. This works, and we still get an integration constant. Okay? So what's f of ty? That's wrong. Go blind when I get up close and I forget what I wrote down. Okay? Yeah, just put the t squared over here, divide by the cosine of t. And then plus an arbitrary constant. That solves the differential equation. And if you write out the differential equation, which is this,
is that the same arbitrary constant?
it's an arbitrary constant. It doesn't matter which one it is, it's still arbitrary.
I mean, there are two c's in your equation.
Well, it's this, oh, you're right. Got up too early or something, okay? Yeah, absolutely. We got a C here, we got a C here. We're not going to have a plus C here. Okay? So the main thing you want to see is test and why this test. If df equals 0, then you get m dy plus n dx equals 0, where n is a partial of f with respect to y, and n is a partial of f with respect to x. That's just your differential. And if that's so, then mx has to equal ny, because mx would be your fyx, and your ny would be your fxy. So you can go back at the steps that I went through in telling you why this is so. Make sure you understand them, then you understand exact equations. Okay? And you see that there's this simple test. If this test holds, then you can proceed to do the integration. And hopefully, you know, the functions are something you can integrate, and they will be. Okay? Unless it's problems I make up, and sometimes I screw it up. Okay? Make sense? So you integrate and you reconcile your g of t and your h of y like this. And then f of ty is c. Whatever function you get out of this integration, set it equal to c and solve for y. Doesn't mean you can necessarily always solve it for y, because it might be an implicit function. Okay? And we might see cases of that, but this is the whole idea of exact equations. It's not a deep idea. It's not a trivial one either. It's one you can understand if you just think through the steps and think this through when you see it. Okay? And I'll prompt you in the homework. Do that. Fair enough?